Hi, I'm DJ Park from Implementation of Computation Group at University of Pennsylvania. Today, I will present fast and flexible FPGA development using hierarchical partial configuration. I think everyone who's watching this video would know FPGA compilation is really slow. How slow? For CPU, GPU, it takes milliseconds, seconds, at most minutes. But for FPGA, it takes at least minutes and hours. And larger designs on larger devices, it could take days. And this is a significant problem because users cannot quickly edit, compile, debug. And if you just imagine a realistic development scenario, you won't just come up with a final solution. You probably come up with something that's barely functional and incrementally add more functionality to it. So it's inevitable that you go through a series of compile, and if a single compile takes hours or days, then that it hugely diminishes a productivity. And why is it so slow? That's because FPGA compile on vendor tool is monolithic. And let's say we have a data flow graph that consists of 4 operators like this, A, B, C, D. If this is a input to a vendor tool, even if it consists of distinct 4 operators like A, B, C, D, the vendor tool will consider this as a large chunk and tries to compile optimize as a whole. And also in placement and routing phase, it exhibits limited parallelism because of a inherent sequential feature of the vendor tool. So do we have a solution to this slow FPGA compile? Thankfully, recently, researchers like us suggested this idea called separate compilation in parallel with the fixed size pages. And this is the list of academic work we've found. And yeah, 2 papers are from FPT that this work will be presented to. So the essence of the idea is that we split the FPGA device into segments and separately compile its segments in parallel. And as one of the direction, some researchers use partial configuration, a technique that partially compile a FPGA device. As all the parallel compile jobs are done, the partial bit streams are loaded on the device and they communicate through network on chip. So this methodology achieves a faster compile because obviously the problem size is smaller than compiling one large chunk. And also by explicitly launching multiple compile jobs in parallel, this approach achieves a better CPU core utilization. And also, let's say you modify something on the design with the vendor tool, you probably need to go through the entire recompile, which could potentially takes hours. But with this approach, let's say if you modify operator D, then operator D is the only part that you need to recompile. So just like a software compile. So are we all good? Is this a perfect approach to program FPGA? What if the sizes of the operators are unbalanced, like this? Then operator D cannot be mapped on predefined PR region. And also, what if the users want to optimize full layer? Then none of the operator cannot be mapped on small PR regions. So the problem with the previous approach is that the pages are fixed size. If you look at the case in the middle, if the pages are large, it obviously reduces the benefit of separate compile because the expected compile speedup is probably 4 times in the case in the middle because you only have 4 pages. So what about the case on the left? Probably the expected speedup is higher because it has more pages. But but it's users' responsibility to manually divide the design into smaller operators. And it can potentially cause a NOC bandwidth bottleneck. So these operators, they communicate through network. And if those are the operators that communicate too heavily, if the too much data is going through that limited channel, that NOC bandwidth could be a bottleneck for the application performance. To resolve all these issues, we proposed this idea, separate compilation in parallel, using hierarchical partial reconfiguration, also known as nested TFX, recently supported by AMD Xilinx. Hierarchical partial reconfiguration is creating a partial region inside a partial region. So if you look at the new framework on the right, you see there are single pages, but you can recombine two single pages to offer double page to the users. Also, you can recombine two double pages to provide quad page to the users. And also octa page or 16 pages also possible. And this data flow graph that wasn't able to be mapped on the previous fixed size page system now can be mapped on our new system because we have quad page to map operator D and double page to map operator B. This is the first framework to exploit hierarchical partial configuration to provide variable size pages like double or quad. We can achieve fine-grained separate compilation with the single pages, if you remember the case on the left. That maximizes the benefit of fast separate compilation. But at the same time, users are not forced to decompose or design into small operators because now they can use double or quad pages. So this is flexible framework. So if you remember the title of this presentation, it's fast and flexible FPGA development, and this is why. This characteristic is really useful in incremental development that I will explain in the next chapter. For the evaluation, I will first explain incremental development scenario with the optical flow benchmark in Rosetta benchmark suite. And then I will talk about the other benchmark and like performance benefits and compile improvements. Let's get down to incremental development scenario first. So the data flow graph in the middle that has 8 operators that's small enough to be fed into single page. And there is one large operator H that's mapped on quad page. And this is a natural decomposition of a optical flow benchmark. With the previous fixed size page system, users had to split operator H into H1, 2, 3, 4 to shrink the size to be able to map on the single page. But now, because we have double or quad page, we can just simply come up with the most natural decomposition and just use it. And just as a hardware engineer, you probably want to quickly start on FPGA and just verify it's working and then incrementally add more functionality. So the fact that you can quickly start from the natural decomposition is really beneficial in productivity. So this was the first step in incremental development. And as a next step, if you think about what we can do to enhance the performance of the application, you see there are red arrows that's labeled 192 bits. That 192 bits, the data width of the data. And because our current network interface is only 32 bits wide, for 192 bits to be transferred onto the NOC, it takes multiple cycles to transfer the data. And then in this case, the communication could be a bottleneck rather than computation for the entire application performance. which is bad. So what can you do? We can simply try merging operators to remove knock bandwidth bottleneck, merging EFGH like this. In this way, then the data do not need to travel over the network. They can just communicate inside the quad page. And one thing to note is that operator ABCDI are already compiled in the previous step. So the newly merged operator EFGH is the only operator that should be compiled in the second step. For the compile time result, we actually have two versions of optical flow, and with the vendor tool, it takes 11 or 12 minutes to compile. With our tool, for the natural decomposition, it took 4 minutes, and the second step, which is merging operator, the second incremental step takes also 4 minutes, and followed by other optimization. If you're interested in, please look at our paper for more details. It generally takes 4 to 5 minutes. And if you look at the step 5 and 6, if you're compiling only the single page, it takes 1 or 2 minutes, which is really fast. But if you are to perform a similar optimization with the vendor tool, you probably start from 11 minutes, 12 minutes for the first step, and the subsequent incremental development step, you probably go through another 10 minutes and another 10 minutes for the next step. So our framework provides fast edit compile optimized environment. And I will talk about the performance benefits and compile improvements of the other benchmarks. So these are the results for all the benchmark, and you see there are 3 rows. The first row is optical flow benchmark, and the second row is rendering, and third row is digit recognition. And you see there are red rows. There are the decomposition that use the previous fixed size page system. So you see that it has only single pages. And the green rows are the decomposition that use our new variable size pages. So you see there are quad pages and double pages. For optical flow benchmark first, you see on the rightmost column, we can achieve application latency over, that's the application performance improvement over previous fixed size pages, 3.6 to 4.9. And this is because as I explained, we removed the knock bandwidth bottleneck by merging operators. And at the same time, it compiles faster than the vendor tool, 2.2 to 2.3. Similarly, rendering and digit recognition, it achieves application performance improvement 1.4, 1.5. And at this time, this is just simply because we use more area for single operator. You see, we use double pages for single operator. And similarly, it compiles faster than the vendor tool. In conclusion, we open source our framework. It's available in our Git repo. And we went through the artifact evaluation. So if you're interested in, just give it a try. We provide variable size pages using hierarchical partial configuration. In the incremental development scenario, a single page takes 1 to 2 minutes, and a quad page takes 4 to 5 minutes for the design that the vendor tool takes 11 to 12 minutes to compile. Thank you.